Geometry lesson on perpendicular bisector of triangles. All right, guys. This is an online lesson, especially during COVID-19. So, uh, if we were to do this construction part, we'll do this in class. But for the sake of the video, let's just imagine how we could do this. Okay. Let's try to use our imagination a little bit. Okay. The circle that contains all vertices of the polygon is circumscribed. So this is not the construction part yet. Okay. So basically what this is saying is that if the circle goes around a triangle and it touches every vertices, right? Like all the vertices, we say that the circle circumscribes the polygon. It could be any, it doesn't have to be a triangle. It could be rectangle, whatever, right? Um, Circum is around, scribe is to write. So we are writing around or drawing around that shape, okay? And then in this particular case, we would call this circle C because its center is point C. So in this case, the circle C is circumscribing the triangle XYZ. And the circle C in this case is called the circle that circumscribes the triangle XYZ. Okay, so it is called the circumcircle of triangle XYZ. And the center of the circle is called the center of the triangle. All right, so that's the definition. And basically, what this says is we're trying to prove the concurrency of triangles perpendicular bisector. Okay. What that means is that when you draw a perpendicular bisector here to each side, right, it will meet at a single point, concurrent point right there. So if it's three or more points or three or more lines are concurrent if they intersect at the same point. The point of intersection is called the point of concurrency, right? Yeah. And if we're in class, we would actually learn to draw this thing, right? And show that it intersects at a single point, and we will find that using a compass, we'll measure from point P to each of the vertices. We'll find that the PA is equal to PB equal to PC. All right. So perpendicular bisector of the sides of the triangle intersect at a point that is equidistant from the vertices of the triangle. That is called the circumcenter theorem. This harkens back to what we learned in the past, right? Do you remember the perpendicular bisector theorem, right? If you have a point, let's say, oh, I don't know, P on a perpendicular bisector, right? Let us say that this right here is a perpendicular bisector of segment AB. So it looks like this. Given this information, what the theorem said was that given this information, like this, these 2 points, oopsie, let me pull that out just a tiny bit right there. Okay, there you go. Are actually congruent. So that was a perpendicular bisector theorem, right? So we're putting all three of them together to say that because of that, right? So this and this, well, sorry, this and this will be perpendicular because of the perpendicular bisector theorem. And for the same reason, this and this is the congruent. But if these two are congruent, these three are congruent, right? And we're done. So that's the main idea behind this, guys. Okay. All right. So we're going to go through the theorem. So if you caught the gist of what I just said, try to write it out on your own. I'm going to show you the pre-written proof of this. You guys ready? All right. Here we go. Anyways, oh, by the way, I forgot to mention, if these is equal, right? If these two are equal, that is the center, we would draw a circle around it. Okay, I forgot to mention that. All right, guys. So basically, we say that P is equidistant from point A to B, right? And then we know that the point P is equidistant from point A and B and A and C in this case, and they're both by the definition of perpendicular bisector, right? Or, yep. No, hold on. It is, sorry. It has to be a perpendicular bisector theorem. Sorry about that. Okay, and that was it. And we know that is if to say that they're equidistant is to say that PA is equal to PC, and we know that the PA in this case is equal to PB. So transit property, we know that the PB is equal to PA, which is equal to PC. So all three of them are the same. We're done. That was it, guys. All right. Okay, so we're gonna use this property, using the property of the perpendicular bisector. So using this diagram, we got ZD, ZE, ZE, ZD, and ZF are perpendicular bisector of ABC. Using the given information, find the length of each segment, and note that the figure is not drawn to scale. Okay. If the point P, okay, we don't even have to memorize this particular formula. Harkening back to what we were, it's implying that because ZD is a perpendicular bisector, this Z is equidistant from the endpoints of the segment A and a B, like this, right? And it also tells you that the ZE is a perpendicular bisector, like right here. So it has to be equidistant from B and a C. So that adds that. So from there, they're all already congruent. But let's go all the way to ZF. And it says ZF is a perpendicular bisector. So Z must be equidistant from the endpoints of the segment CA, which means that these two are the same. Okay. All right. Let's go through this. And on top of that, these two are the same. These two are the same. And these two are the same. Okay, because they're perpendicular bisectors, right? So what's FZ? FZ is 36. Okay. And ZA is 85. This is 85. And then we know that the AB is 150. I don't know why, but because these are half of that distance, that AD here must be 75. Like normally when you give your graph, we don't draw this line over here though, but we do put the number usually around the middle spot right there, right? So 75, the middle of AD. Okay, that's generally how we write it. So the question is, they're asking you to find AD. Well, we already found that, right? So we would say in this particular case, let's see, there you go. Shift it up just a tiny bit so I can write this. So we know that, oh, there you go. All right. AD is 1/2 of AB. Why? Because D is a midpoint, right, of the segment AB. Therefore, the AD must be half of the entire length AB. And we know that the AB is equal to 150. And this is kind of work that I would like to see, guys. Okay. And what is a ZB in this case, right? ZB. How do we find that? Wait a minute. Isn't ZB, according to what we just learned, same thing as ZC, and it's also equal to ZA, and ZA just happens to be 85 that was given to us. Yeah, and that was it, guys. That's all that there was. Okay, make that a little bigger, so perhaps you can see it better this way. Okay, guys, that was it. All right, guys, let's move on to the next question. Find the circumcenter of the coordinate, right? Blah, 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 blah. What exactly was the circumcenter again? Okay, let's go back. The circumcenter. Okay. Was it early? No, sorry. Interesting. All right, guys. Here's the circumcenter. Yeah, I was wondering, like, the book usually used the word, but didn't really define it, okay? The circumcenter is right here. Let me write that over here, guys, right? So if the intersection of all that, right, is so we're going to say that the P is called the concurrent point of the perpendicular bisector is called the circumcenter. Which is the concurrent point of perpendicular bisectors. Okay, guys? All right, there it goes. Okay, so let's get started with the last question. Find the circumcenter of the coordinate plane, and they give us a coordinate. The Q is 3, 4. 1, 2, 3, 4. So that's the Q. And the R is 7, 4, which is here. That's R. And S is 3, -2. So that's 3, -2. Well, lucky for us, this is what? A right triangle. Okay. So in order to find the circumcenter, we're looking for what again? That's right. Concurrent point of perpendicular bisectors. Let's zoom in. Here's the thing, because all three perpendicular bisectors have the same point, we only need to do two, right? In this particular case, the perpendicular bisector of the QR, without using any special tools, is here. Because QR is horizontal, we are going to draw a vertical line. So that is a perpendicular bisector like this. For QS, the distance is like what is it? Let's count. 1, 2, 3, 4, 5, 6. Half of that is 3. Just 1, 2, 3. It's right here. And then this distance and that distance is the same. And because the QS is vertical, the horizontal would be perpendicular, and it connects it right there. Now, let's take a look at that one. Okay. So that right there from here is 1, 2, 1, 2, 3. So that is 2 and a 3. So let's call this, I don't know, P, let's say, right? So PS, let's just check it out. Squared is equal to 3 squared plus 2 squared. 9 plus 4 is 13. So PS is square root of 13. And then RP squared is the same thing. 1, 2. 1, 2, 3. 2 squared plus 3 squared, that is 13. RP is square root of 13. Oh my gosh. So that distance right here is the same. Clearly, that is the same. Now, we could go ahead and just keep doing it, but it's not necessary, but we'll do it anyways, right? So how do I draw a perpendicular line? Okay, well, what is my slope? It goes up 1, 2, 3, and across 2. So we got to do the negative reciprocal, do we not? So we go up 2, but left 3. 1, 2, 3. This point right there. So what I'm going to do is 1, 2, 3 right there. There you go. Now that is perpendicular right here, isn't it? So, and that certainly intersects at point P. Is that right, guys? All right. So that's the kind of work that I like to see. And we could say that the point P, all right, is the circumcenter with the coordinate. And I believe that's 5, 1. Yes, it is. 5, 1. All right, guys, that is it. Okay, let's take a look at my pre-made answers to see if you get the same answer. Yes, we do. Good. The drawing is about the same. That was slightly more colorful last year. And here is the same thing. Okay. All right, guys. So that wraps up today's lesson. And I will see you in the next class. Have a good night.